So this check-in here, it's got a 600 kilogram car coming to a stop. We might as well write this down. Probably gonna have to use it. Mass is 600 kilograms. Its brakes do 4,800 joules of work to stop it. Okay, so this is an energy question because it's talking about joules and work. So we know that's joules. It says it's work. I'm not gonna write W equals because it's probably gonna ask for something that it's gonna convert from or to. So I'll just say energy before we figure out what kind of energy, kinetic energy or potential energy or work it is. I'll just say energy is 4,800 joules. What was its velocity before it stopped? All right, so since it's asking for velocity, that means that the only way we can get velocity with energy is using that kinetic energy formula. That's the only one with a V in it. Ke equals 1/2 mv squared. So I'm gonna switch markers. Here we go. Okay, new marker. 1/2 mv squared. So that 4,800 joules then that gave us with that work, that used to be kinetic energy apparently. So I'll say 4,800 joules in kinetic energy. So what happened was it was going fast and then the brakes stopped it and the brakes heated up from stopping it. So they just converted that. Well, I guess if they did that much work to stop it, that's how much like energy they spent squeezing to stop the car. But they would have heated up, so they did that much work to get rid of that 4,800 joules of kinetic energy, and then that kinetic energy turned into thermal energy because those brakes heated up. So that's where that kinetic energy came from, or that's where it started from. It ended up as work in thermal energy. The mass is 600 kilograms of this car, and velocity is what we're looking for. Cool. Okay, so I can do some of this already. What's 1/2 times 600? 300, there we go. I was about to spin the wheel there. 300 v squared. Ooh, we can do this, we can do this. So we needed to say v squared, that's not a square. We needed to say v squared and then we needed to say just v. So it says v squared times 300, so I'll divide by both sides by 300. Oh man, I don't know what 48 divided by 3 is. Maybe I should, I don't know. Maybe I do. Do I? I don't know. Well, I know what 48 divided by 6 is. What's 48 divided by 6? Well, I'm going to spin the wheel. I'm going to spin it. Colton, what's 48 divided by 6? Oh, 6 times what is 48? Anybody else?
4,800 divided by 316.
Yeah, but 6 times 8 is 48, right? So that would make sense then that 3 times 16 would be 48, since 3 is half of 6 and 16 is twice of 8. Anyway, yeah, so 4,800 divided by 300 would be 16. And I did this on purpose so that we can get the v easy here. So v squared is 16. The square root of v squared is v. And what's the square root of 16? I know, okay, you know what the square root of 16 is 4. So that's the velocity, so it's in meters per second because it's velocity. And there we go, a bunch of energy things. So you can tell us a lot of these check-ins and closings have been about energy stuff like this. There's going to be some questions on the CTBA about that. That's what that means. So today we're doing our first calculations. I mean, we did the quiz yesterday, but the first today's assignment is only inelastic collisions calculations. So I'm going to do this top question here. This was I like this question because it's got a falcon coming down and grabbing a grackle out of the air, and then the pair move together, and you have to calculate their new speed. And you know, one of those nature questions or whatever, I guess. Anyway, all right. I'm just thinking about the purple marker, I think. What do you think, purple or green? Purple. So we got a 0.5 kilogram Falcon, object 1. So got that, M1 is 0.5, going 20 meters per second. That's V1, 20. It grabs onto a 0.1 kilogram Grackle, that's smaller than the Falcon. That's mass 2. And that's going 8 meters per second. And that's V2. Cool, I got everything already there. Now this is an inelastic collision. If you've noticed, every time it gives you the formulas, it says elastic collisions bounce apart. That was that first lab that we did, where the cards bounced apart. And inelastic collisions stick together. And that was the second lab we did. Make sure if y'all had trouble doing the lab at home, tell me so I can maybe give you some advice or fix you up. So these are all inelastic today. You can see how the formula is different. There were 2 cards before, but afterwards they stuck together. You can see you add up the masses because they're together now. So all right, inelastic collision, that means they stick together. It says, how fast did the pair move together after the collision? So that means in the after variables, we're looking for how fast, looking for V here. And I said V3 because it's not object 1 or object 2 anymore. They're not separate. It's like a new object that's made of both of them, so that's why I said V3. It's not really a third object, but kind of, pretty much. And these inelastic questions are easier than the other ones because it's always going to ask for how fast are they moving together afterward, and the only thing that you have to mess with afterward is that velocity, because the masses always stay the same. Mass 1 is 0.5, mass 1 is still 0.5. Mass 2 is 0.1, mass 2 is still 0.1. And now we gotta plug them in. So before 0.5 kilograms times 20 meters per second, and mass 2 is 0.1 kilograms times 8 meters per second. Mass 1 plus mass 2. Oh, they're the same. Mass 1 is still 0.5 kilograms. Oh, no, I forgot my plus sign. Mass 1 plus mass 2 is 0.1 kilograms. And we're looking for V3 over here. All right, 0.5 times 20, that's 10. 0.1 times 8, that's 0.8. And 0.5 plus 0.1, that's 0.6. V3. Let's consolidate. 10 plus 0.8 is 10.8. And I gotta divide that by 0.6. I don't know what that is. Gonna have to use a calculator. Anyway, we wanted to say equals V3. It says V3 times 0.6, so we'll divide both sides by 0.6. And I guess I gotta calculate. I don't know what that is. I don't know what 108 divided by 6 is. I don't know what 100 divided by 6 is. So 10.8 divided by 0.6. 18 apparently. Should I have figured that out? I don't know. That's 18 and it's velocity, so it's meters per second. Alright. There we go. So those are a little easier than the other momentum problems. On Tuesday, because Mondays are not allowed anymore, I guess. On Tuesday we're doing an assignment with some of each on it. Some are elastic, some are inelastic. You've got to figure out which are which, because some bounce apart, that's elastic. Some stick together, that's inelastic. Today though, they're all like this. They're all inelastic. So please try out this assignment here. People at home, if you haven't done your elastic lab yet, today's the last day. I'm shutting the assignment down this afternoon, so get it done if you can.